Okay, let's dive right in. We've all seen these incredible leaps robots are making in manipulation, right? Learning to pick things up, pour liquids, open doors. It's pretty amazing stuff.
Absolutely. The policies they're learning are getting really capable for very specific tasks. But, there's often a catch.
Yeah, what's that?
Well, usually they're trained in a really fixed setup, like the robot arm might always start in the exact same spot relative to the table, or the camera view is always identical.
Right. So the robot gets really good at, say, turning on that faucet, but only if its base is parked precisely here and the camera is looking just so.
Exactly. But then what happens when you take that super skilled policy and put it on a mobile robot? One that can, drive around a room.
Suddenly the game changes. The robot's base isn't in that perfect spot anymore. The camera angle is totally different. The thing it needs to grab might be way over there.
And boom, that policy, which was trained for such a narrow window of conditions, it struggles or fails completely. It's kind of like having this amazing, complex recipe that only works in your perfectly set up home kitchen and then trying to make it camping.
Ah, yeah, good analogy. The visual input, the space the arm can actually reach, it's
Yeah.
all drifted outside what the policy expects, outside its comfort zone.
The initial condition, the starting state it needs to kick off that sequence of moves is just wrong.
Okay, so you might think we'll just train the policy to work from anywhere, but that sounds like a massive headache,
Oh,
data-wise.
it's a huge one. Retraining these manipulation skills for every possible starting position, every viewpoint, every environment, it's incredibly costly. You need just tons and tons of data.
Okay, so that's probably out. What about just telling the robot to drive near the object? Like, use standard navigation, go towards the microwave handle.
Yeah, that's what typical navigation systems do. They get the robot into the general vicinity. But, and this is key to the research we're looking at, just being near the target isn't good enough for these manipulation policies. Why not? If it can see the handle. Well, it might see it, sure, but maybe not from the right distance or the right angle. The policy was trained expecting a certain perspective, a certain reachability. If the robot navigates too close or too far or sideways, the handle might be visible, but effectively unreachable or unrecognizable for that specific, finicky manipulation routine.
Ah, okay, so this brings us neatly to the core problem we're tackling in this deep dive. Policy mobilization. What exactly does that mean?
Policy mobilization, essentially, is the challenge of getting a mobile robot to intelligently find the right starting position, the right base pose, in a new, maybe completely unseen environment.
The right pose, so the...
So that a manipulation policy, one that was originally trained with maybe limited viewpoints or starting conditions, can actually succeed at its task from that specific spot.
Got it. So instead of making the manipulation part infinitely flexible, which is, like you said, a data nightmare,
Right.
we focus on making the robot smart enough to find the perfect starting line for the existing policy wherever it needs to run.
Precisely. It decouples the problem. Step 1. Navigate smartly to the right pose. Step 2. Execute the policy you already have. The trick is making Step 1 the navigation aware of what Step 2 needs.
And to really dig into this systematically, the researchers developed something called the Mobi framework.
Yep, maybe op. It's not just one specific algorithm, but more like a structured way to study this whole policy mobilization problem. It gives us tools to measure how tricky mobilization is for different tasks, sets up benchmark challenges, and lets it compare different approaches fairly.
Okay, so how do you measure how hard it is to, mobilize a policy? Some tasks seem like they'd need much more precise starting points than others, turning a tiny knob versus closing a big drawer, for instance.
Exactly. And they came up with two key metrics to quantify that. The first one is spatial mobilization feasibility, which they call PHE. Think of it as spatial wiggle room.
Oh, will room.
Yeah, how far can the robot's base physically move away from the ideal training spot before the policy's success rate drops by half? It's measured in meters.
Okay, so a higher phi means the policy is more forgiving spatially.
That's it. And their examples really highlight this. Like you said, turn on stove. Turning a small, precise knob has a very low phi, just 0.031 meters. Basically, move the robot more than 3 centimeters off target, and you're likely to fail.
Wow, tiny margin.
Very tiny. But compare that to closed drawer. That task has a much higher phi, 0.206 meters, almost 21 centimeters of wiggle room.
Makes perfect sense. Closing a drawer is just less demanding on exact positioning. What's the second metric then?
The second one tackles the visual side, visual mobilization feasibility, or SV. This measures roughly how much of the target object is clearly visible from good viewpoints near that optimal pose.
So if the object is often partly hidden or looks really small even when you're in the right zone.
Then it's visually harder to mobilize.
Yeah.
Even if you're physically in the right area, if the visual cues aren't clear or consistent from slightly different angles, a vision-based system will struggle to find that perfect alignment for the policy.
And are these two linked? Like, is spatially hard always visually hard?
Interestingly, no. They found they aren't necessarily correlated. Remember, close drawer, spatially easy, high five.
Yeah.
It turned out to be the most visually difficult task they studied, with a low FE. Maybe the handle blends in or the perspective changes dramatically with small movements.
Huh. So you really need to consider both the physical precision and the visual clarity needed by the policy. Knowing phi and SV tells you why mobilizing a specific task might be tough.
Exactly. It gives you a much clearer picture of the challenge.
So how do they use this framework to test different approaches? What kind of setup?
They built a simulation task suite using RoboCasa, which is a benchmark for household chores. They focused on 5 tasks: close door, turn on faucet, turn on microwave, close drawer, and turn on stove.
Then crucially,
The policies for these tasks were not originally built for mobile robots. They were trained from limited, fixed starting points. The real test was deploying these policies in completely new room layouts with different textures and appearances that the policy had never seen during training.
okay, that sounds like a properly tough test bed. How did the existing methods, the baselines, fare?
They looked at a couple of categories. First up were the non-policy aware baselines,
Meaning?
meaning methods that just navigate to the object's location without considering the specific needs of the manipulation policy that's supposed to run next. Think standard navigation planners like Leland or VLFM, which they tested.
Just get me near the microwave.
Pretty much. And the
But-
result,
Let me guess. Not great.
you got it. They often failed. They'd successfully drive the robot to the object, but maybe too close or at a weird angle, putting the object outside the manipulation policy's trained sweet spot. It really confirmed that just getting near isn't enough. The final pose has to be right for the policy.
Okay, validates the core problem. What about approaches that do try to be policy aware?
They tested a representative one, training a single big policy using imitation learning, they call it BCW-nav, that tries to learn both the navigation and the manipulation together, end to end.
Ah, the one policy to rule them all approach. Sounds good in theory.
It does. But the reality was, well, first it needed way more data. In their sims, it used 5 times the demonstrations compared to just training the manipulation part.
5 times. Wow.
Yeah, 1,500 demos versus 300. And even with all that extra data, it really struggled to generalize when they put it into those totally new, unseen room layouts.
So even throwing lots of data at a single end-to-end policy doesn't necessarily make it robust to new environments.
That's what they found. It really highlights why this idea of decoupling smart navigation first, then execute the manipulation policy offered by the Mobi framework is such an interesting direction. It might be more practical than trying to train one giant do-everything policy.
Okay, this is where it gets really interesting then. The baselines have issues. What's the novel method these researchers propose to actually solve policy mobilization within this Mobi framework?
Right, so they developed a specific method designed to be policy-aware, work in novel environments, and crucially do it without needing tons of extra training data for the manipulation skill itself.
Sounds promising. What does it need to start with? What are the assumptions?
Okay, a few key things. It needs access to the initial observation images from the original manipulation policy's training data.
Just the first frames?
Yeah, basically examples of what the scene looked like right at the beginning of successful runs during training. Not the whole policy, not all the trajectory data, just those starting views.
Okay, so visual examples of good starts. What else?
The robot needs to be able to explore the new scene first, look around and build a map. And they assume a fixed camera position relative to the robot's base, though they mention that could potentially be relaxed later.
Got it. Examples of good views and the ability to map the new place. So how does it actually find the right pose? Walk us through the steps.
Okay, step 1. Represent the new scene. The robot drives around a bit, collecting RGB and depth images, and uses that data to build a 3D model. Specifically, they use 3D Gaussian splatting, or 3DGS.
Ah, 3D Gaussian splatting. That's that really cool newer technique that creates super realistic 3D representations you can render new views from, right?
Exactly. Builds this high-fidelity 3D model, which is critical because it lets the system then virtually render what the camera would see from any potential robot position within that mapped area without actually having to drive there.
Nifty. So build a really good virtual copy of the new room. Step 2.
Step 2 is evaluating potential robot poses. This is really the core of their policy-aware strategy. For any hypothetical robot-based pose, let's call it P, they calculate a hybrid score function, KP. This function checks three crucial things.
Okay, first check.
First check is the rendered view in distribution. They call this KID. So it uses the 3D model to render an image from that hypothetical pose P. Then it extracts visual features from this rendered image specifically, dyno-dense descriptors, and compares them to the features from those initial training images, those good starts we talked about.
So it's asking, does this potential view look and feel like the views where the policy succeeded during training, using those dyno features to compare?
Precisely. It's checking for visual similarity in a way that captures important contextual cues, not just, say, pixel values. And they found dyno descriptors work really well for this.
Okay, so check one. Does the view look familiar to the policy? What's check two?
Check two. Is the object visible? They call this COBJ. Even if the general view looks right, the target object itself needs to be clearly visible for the policy to work. They use a vision language model, mini CPM-v2 in this case.
Like an AI that understands images and text prompts.
Exactly. They basically ask it, is the target object, like faucet handle, clearly visible in this rendered image?
Got it. View looks right, and the target object is actually there and visible. Third check.
Third check is simpler. Is the pose collision-free? Tico. Just a safety check using the map built in step 1, would placing the robot base at pose P cause it to bump into anything?
Makes sense. Safety first. So how does the final score KP work?
It's pretty strict. The score KP is high only if all three checks pass. The pose is collision-free, the object is visible, and the view is visually in distribution according to those dyno features. If any of those conditions fail, the score is 0.
Okay, so it has to tick all the boxes to be considered a potentially good spot. Build the virtual scene, then for any potential spot, virtually look and score it based on policy friendliness, object visibility, and safety. How does it find the best spot among all possibilities?
Right, so step 3 is finding the best pose. Now, this score function, KP, can be complex. It might not be smooth. A small move could suddenly make the object visible or occluded, causing the score to jump from 0 to high. So standard optimization methods that rely on smooth gradients don't work well.
So they need a different approach.
Yeah, they use Bayesian optimization, or BO.
Ah, Bayesian optimization. That's one of those clever search methods for finding the best value of a function when it's expensive to evaluate, or, like here, non-smooth, right?
Exactly. BO is really good at exploring the space of possible poses efficiently. It samples a pose, gets its score using KP, uses that result to update a probabilistic model of how the score behaves across the pose space, and then intelligently decides where to sample next. It balances exploring new, unknown areas and exploiting areas that already look promising.
So it smartly searches through the possible robot-based positions, guided by the hybrid score, to find the one most likely to let the policy succeed.
That's the whole process in a nutshell. Explore and map, then use BO to search for the highest scoring pose by virtually rendering views and checking them against the policy's needs, object visibility, and safety constraints.
It's a really neat combination of mapping, visual understanding, and smart search. So the big question, did it actually work? What did the results show?
The results were pretty compelling. In the simulation experiments across those 5 RoboCasa tasks, their method significantly beat all the baselines. It was much better at finding starting poses that actually led to the manipulation policy succeeding.
How much better?
Get this, in 4 out of the 5 tasks, the success rate using their mobilization method was almost the same as, or sometimes even slightly better than, running the original policy when it was started perfectly, just with a tiny 5-centimeter nudge from its ideal training pose.
Wow, that's really impressive. It means their method can guide the robot to a starting point that's practically as good as the one the policy was explicitly trained for, even in a totally new room.
Exactly. It shows it can really nail down that required initial condition.
And did they see the connection to those feasibility metrics, phi and SV, play out in the results?
Yes, absolutely. And it really validated the metrics, the non-policy-aware baselines, the ones that just navigated nearby. They struggled the most on tasks with low spatial feasibility, low phi, where precise positioning was critical.
Makes sense.
And their proposed method did great overall, but its performance saw a small dip on closed drawer, which was that visually challenging task with low SV.
Right, the one that was easy spatially but hard visually.
Yeah. Which also makes sense because their method relies heavily on getting the visual input right. If the visual cues are inherently difficult for a task, even a smart visual-based method will find it tougher. So the metrics did seem predictive of the difficult.
And you mentioned those dyno-dense descriptors were important for judging the view. Did they confirm that?
They did. They ran an ablation study, basically. They tried running their method without dyno or using simpler visual features instead, and the performance dropped quite a bit.
So what does that tell us?
It suggests that these dyno descriptors are really capturing the right kind of subtle visual information. Things like object context, relative scale, maybe even lighting nuances that are needed to accurately judge if a view from a new place truly matches the look and feel of the views the policy learned to succeed from. Simpler features just weren't catching that nuance.
Okay, strong simulation results. But, the real world is messy. How did it fare on an actual physical robot?
That's the crucial test, right? They put on a real mobile manipulator in a mock-up grocery store setting. Pretty cool environment. They tested 3 tasks: picking up a bag of chips, grabbing a roll of paper towels, which was a bimanual task, using both arms, and pouring canned tomatoes.
Challenging real-world type tasks. Who did they compare against?
They compared their method against that end-to-end BCW nav baseline and also against a human baseline.
A human baseline. How did that work?
They had people manually drive the robot using a joystick to what they thought was the best starting position for the task, just based on looking at the scene. Then they'd run the manipulation policy from there.
Fascinating comparison. What happened in the real world?
The results were really striking. The human operators, well, they could get the robot near the object, obviously. But because they didn't have the insider knowledge of the manipulation policy's specific visual or spatial needs.
They didn't know the exact sweet spot the policy wanted.
Exactly. So the poses they chose often weren't quite right, and the manipulation policy frequently failed when run from those human-chosen spots. The BCW nav baseline did better than the humans, but still had a lot of failures, and significantly quite a few collisions with the environment or the target object. It struggled to consistently find the right, safe pose.
Okay, so humans are good at nearby. BCW nav is better but imperfect, and their proposed method.
Their method achieved the highest success rates by a clear margin across all 3 real-world tasks. But here's the kicker, the really big takeaway.
Yeah.
Their method resulted in 0 collisions.
0 collisions. In the real world, doing manipulation.
0 collisions compared to significant collision rates for both the BCW nav and even the human baseline.
That is huge. It's not just about success rate, it's about safety and reliability. 0 collisions strongly suggest the method is finding poses that are not only effective for the policy, but also genuinely safe in the cluttered real world.
It really validates that it can find those good poses reliably, even better than a human just eyeballing it, because it's leveraging that knowledge from the policy's training data.
You also mentioned some other cool demos they showed, beyond single tasks.
Yeah, they showed some really nice qualitative examples. They demonstrated chaining skills. The robot would use the method to find a pose to close one drawer, succeed, then immediately rerun the optimization to find the pose for the next drawer and close that one too.
Oh, neat. So it can remobilize on the fly.
Yep. They showed 0-shot generalization, just dropping the robot in a completely new room layout it had never seen. And the method worked. It handled large spaces like that 6x10 meter grocery store scene. And they even showed it adapting to object height variations by including the camera's height as something to optimize during the pose search.
That ability to chain tasks and adapt to variations, that really starts to paint a picture of more useful mobile robots.
Absolutely. It shows a practical path towards taking this growing library of manipulation skills, many perhaps trained in very specific setups, and actually deploying them usefully on mobile platforms out in the world without needing that massive retraining effort for every new situation.
Okay, sounds incredibly promising. But like any research, there must be limitations or areas for future work, right?
Of course. They pointed out a few key ones. Currently, it assumes the scene is static. If things move around after the robot has mapped and found its pose, the 3D GS model would be out of date, which could cause problems, especially if you're chaining tasks.
Right, dynamic environments are always tricky.
It does need access to those initial observation images from the policy training. They argue it's much less data than training end-to-end, but it's still a requirement. The focus right now is on mobilizing existing single-task policies, not creating generalist policies from scratch. And the core method assumes a fixed transformation between the robot base and the camera, although they did show that camera height optimization as a first step towards relaxing that.
Okay, so handling dynamic scenes, Maybe reducing the reliance on initial images, extending to multitask policies, and more flexible camera setups. Those sound like natural next steps.
Definitely. But even with those current limitations, it feels like a really significant contribution.
Yeah, it really seems like the Mobi framework gives us a solid way to think about and measure this crucial problem, and their specific method provides a powerful data-efficient solution.
It's a smart blend of modern mapping, vision, and optimization to bridge that gap between skill but static manipulation and truly useful mobile manipulation in diverse settings.
It really feels like a key piece of the puzzle for making mobile robots more versatile and capable.
It offers a concrete way to leverage all the progress being made in manipulation learning and actually get those skills off the lab bench or the fixed factory arm and out into the real world on robots that move.
So thinking bigger picture, just imagine the sheer number of manipulation skills being developed right now. Skills for assembling parts, sorting objects, carefully handling delicate items. Many are stuck in fixed setups.
Right.
What if this kind of policy mobilization approach allows us to easily take those skills and put them onto a mobile robot that can navigate a home or a warehouse or maybe even a hospital or a store?
It could genuinely unlock a whole new level of capability for mobile robots, making it feasible to equip them with these really intricate specialized skills that were previously just too hard or too costly to adapt to new environments on the fly.
What kinds of complex, fiddly tasks could we realistically see mobile robots tackling in the near future if they can reliably figure out exactly where to stand to get the job done? That's definitely something interesting to ponder.